I would like to show you the possibilities with Simulating Annealing Studio. Let's open a problem, for example, traveling salesman problem. At first, here it is, the blue dots are the cities, the edges represent the route of the traveling salesman, the current energy, the current sum of the edge length are over 2000. Of course, this is not an optimal route, but let's call Simulated Annealing by pushing the green button, and it will plan us a much better route for the traveling salesman. Here the current energy is much lower than before, and it also produces us a number of snapshots, so we can check that on different points of the process what was the position. So we started from here, and from step by step we see that we also see the current energy, that we see the step by step how we lowered this. If I push the best button here, then I will get the best current energy, which is the lowest one, of course. It also produced us some valuable diagnostics data. Let's just quickly check the global metrics, which is true for all the snapshots. So global metrics will say that we made almost 6 million iterations. Sorry, 60 million iterations. The speed was over 11 million iterations per second. We made that many acceptances, that many up energy changes. The characteristic of the simulated annealing meta heuristic is that it sometimes can accept moves that increase the energy. This way it is checking the solution space much more broader than, for example, a greedy algorithm, which never accepts a candidate move which increase the energy. So it sometimes accepts such moves, and this way it sees a lot more thing, and that's why the overall eventual solution is better than for a simple greedy algorithm. And here is just one more thing, the all-time best, which has nothing to do with our current run. This says that for this starting position, at some point earlier, the Simulated Annealing Studio made a solution of this energy. So if we check the current best, we are quite close to the all-time best. We can also load the all-time best if we are interested in. Yeah, this is the all-time best so far. Okay, let's open another position a bit larger with 1,000 cities. And let's check the other possibilities what we can choose. The most important one is the resource policy. If I just hit the green button, then it will take 5 seconds to calculate and find this solution. It finds this solution. Let's go back to the starting position, and let's say that, okay, but I will give you now 1 second. Then it is much quicker, and it finds a bit worse solution as expected. If we give it an hour, then it will run for an hour, and it will find a much better solution. Of course, we will not have time to wait for it, so I will just stop it, but you can write anything for here. Instead of time, you can set iteration, which will mean that make that many iterations. Of course, iteration is not that well defined as a time, as for different problems iteration can have different time needs. So that's not that well defined and not that plannable than time. Let's check the other policies. The default acceptance policy is Metropolis, which is a very well-known acceptance policy for simulated annealing, but the other possibility is greedy algorithm. We already talked about it. And if we check, if I run with a greedy algorithm, okay, not for an hour but for a second, then there will be no up energy changes as expected. Okay, but it is usually not give a very great solution, so let's use the Metropolis acceptance policy. In cooling policy, you can also choose a different kind of cooling schedules. You can define the T0, the temperature at the starting point. This is basically a scaling factor. If it is larger, then the process will make more explorations. If it is smaller, see what happens here. It will accept anything basically for most of the time. If you make it smaller, then it will be much more conservative than before. And yes, so if it is 0, then basically you will get the greedy algorithm back. The default value is 1, but yes, this is a scaling factor. Move selector policy is also a very interesting thing. Basically, by default, we are generating k move candidates, 1 move candidates, but if we write here 100, then we will, in every iteration, we will generate 100 move candidates, and from the 100 move candidates, we will choose the very best out of the 100, and check if the algorithm will accept it or not. So this way, for example, let me just go back here. So if k is 1, then you will see that the acceptance ratio is much lower, generally speaking, than if it is 100, because the recommended moves are much better if they are the best out of 100 candidates. Monitoring options are defined in this row. These are for diagnostic purposes, so it has nothing to do with the outcome. How many snapshots we want to make, some memory limit to make it more safer, and so on. Beside of snapshot, we can choose all, but I don't really recommend it. Then it will make a snapshot whenever the position changes, but this can easily use too much memory. So I recommend it for debugging purposes, but generally snapshots are just fine. Random seed is time-based by default, but one can also set it explicitly. This is also more interesting for those who want to debug some process, but for general users, time-based random seed is good. Finally, a very important value is parallel threads. So far we only calculated on one thread, as you see, but we can write here 10, and then we will calculate on 10 parallel threads. We will call the simulated annealing process, and out of the 10 processes, we will choose the best one. So this is a great feature. And finally, here are the repeats, which basically says that just repeat everything which is defined here, repeat it that many times. So by default it is 1, but if I set it to 2, then as you see, we will make everything 2 times. So basically then we will choose not from 10 processes the best one, but from 20. Yeah, that are the main features of the Simulated Annealing Studio. Yeah, let load the all-time best. You see that we are not that quite right now, close to it. That's the all-time best. What other possibilities are there? So, for example, you can save any position if you want. I just save it. Later I can open it. I can zoom into the to the plot. Yes. So to summarize, using this Simulated Annealing Studio, you will get a tool which I hope quite conveniently help you find a good solution for your problem. It will help you use parallel threads. It will give you some diagnostic data. It will track all-time best solution. So this is what you get from it. And I think at that point you might have at least two very valid questions. One is that, okay, I would like to use it, but these are predefined positions and I have a traveling salesman problems of my own. How can I use the studio? So basically, if you just check how the problem is serialized, then you will be easily be able to define your own problem. So here is how the traveling salesman position is defined. First comes the problem tag and then the coordinates of the points. So it is very easy to use it for your own problems. And the other even more valid question, of course, is that, okay, but I would like to use simulated annealing, but for a completely different problem, not for the traveling salesman and not for any problems defined in the repo so far. And it is also possible. I plan the repo so that it is scalable in this direction for other problems, but I will show it in another video.